we need to switch over to Dave's presentation, where I know he can talk a little bit more about antennas. But thank you all for the questions. Thank you, Ralph. Thank you, Jim. Dave, are you ready to go?
I am. Thanks.
Excellent.
Thanks, Michael.
Thank you. All right,
Okay.
The floor is yours, and Kirby will drive the slides for you.
Sure. Thank you. My name is Dave Copeland. I will talk through a summary of our communications trades on both spacecraft and the ground side. I do want to recognize Reza Ashtari, who's got a lot of the work that you're going to be seeing in this presentation. And go to the next slide, please. Okay, to start with, the trade space for a telecommunications system quite often just comes down to looking at the terms in the link equation showing here. We know that data rate goes as the received signal to noise ratio. So it's going to go as the inverse of the distance squared. It's going to go directly as transmit output power. Should go as the choice of the operating frequency squared. If you treat the antennas as apertures, there's always second order effects here though. And that trade never quite looks as clean as you'd think it would. The spacecraft transmitting aperture figures into this, and tied to that is always how well can we point it. And then of course the ground station aperture and its performance. Next slide, please. So mapping that into the actual trades that we're looking here. We started with pointing because this is a major driver for us here, in that we can build very high gain antennas. If we can't point them accurately enough, then they do us no good. So the trade here is, do we count on a body fixed system such as was used in New Horizons, or do we go more complicated and actually have secondary pointing on the spacecraft for the main beam coming off the high gain? If we can point tighter, then we can use a higher directivity, higher gain on that aperture. Now the mapping of that directivity to the physical size of the aperture is the frequency decision. So X and Ka are obvious choices for their use in deep space. Optical is also in that mix as well. It becomes the ultimate trade sort of to pointing there. The aperture size and the technology that is used. So Tony, speaking to your question here, we looked at both solid antennas and the other technologies that are available, including mesh or membrane reflectors and deployable reflectors. And this sets the mass that we're getting for the required gain. Ground station capability, the DSN is the obvious choice to go with here. You'll see here that for operations beyond sort of the 70 AU timeframe, we're counting on actually going beyond the DSN. We need more aperture, and the more aperture we can get on the ground, the better. So we're using here as our notional case if we were to actually use the next generation VLA. And then finally, how do we scale the transmitter power on the spacecraft? So the downlink is a major DC power draw, and how much power we can devote to that is dependent on the RTGs and their degradation over time. So, do we scale it to just 50 years, or do we try to see what we can do to exploit going beyond that 50-year lifetime? Next slide, please. Okay, this is the baseline system, and this is for options 1 and 2, the Jupiter gravity assist options. And you can see sort of the trajectory we're taking through that trade space. We're counting on using a 5-meter high gain antenna with complementary antennas, medium gain and low gain, that primarily come into play while we're still well within the solar system. An RF power of 52 watts, which is counting on drawing a DC power of 90 watts. Overall, the subsystem mass is about 73 kilograms, and it is dominated by that high gain. If we take a look at deployable technologies or membrane technologies for those antennas, and those have flown at this point, we can bring that mass down. And you can see the data rates that we can achieve with this system, first at about 375 AU, which lines up roughly to the 50-year point, and then going all the way out to that 1,000 AU target. Next slide, please. you switch to the next slide, please?
I did. Did it should be showing slide 9 if you look in the lower right corner.
I think we're still seeing slide 8. I'm seeing the baseline telecom subsystem slide.
Which one did you intend? Are you now on slide 40?
Oh, Kirby, could you perhaps
I don't
share and
understand.
reshare?
Yeah, maybe that's it.
Thanks.
Not sure. Haven't run into that problem before.
It's a telecom problem. What can I say? Actually, can you go to slide 39? There we go. Thank you. Okay.
Yes.
So talking about our baseline telecom ConOps. So we laid out a plan for how we felt we would basically be talking to the spacecraft during the mission life, and how would we trade off the different ground station apertures that are available to us. So early operations, in fact, out for the first 10 years of the mission, we're assuming you're on the DSN. As we're crossing that 70 AU boundary, we would transition over to the NGVLA. And you can see to the right there, then the total data volume per week that we're predicting now that you would get down following this ConOps. Go to the next slide, please. Okay, so why this baseline? This is a very high TRL design for the spacecraft. We could effectively build this system right now. So we're minimizing the risk that's on the spacecraft, but full disclosure, in so doing, we're moving risk down to the ground. We really are counting on there being, this development now for a greater aperture on the ground. The pointed constraints for this design fit within the capabilities of the spacecraft for a simple body fixed antenna. We're not having to bring the added complication of trying to do secondary beam control on the spacecraft. The ground assets for this mission, they exist now and for the first 10 years of the mission. There is planning now for developing our ground assets, albeit not in our community, in the radio astronomy community, that would be able to provide performance out to 1,000 AU. Granted, one point to recognize is what's the funding status of that. This is an area where I would really like to see our community and the radio astronomy community working together more. Next slide, please. Okay, this is one point that Pontus brought up earlier in the week is what's the impact of the target choice on the performance we're going to see at the ground station. So again, using the NGVLA as our national case, one thing to consider is that it is a Northern Hemisphere asset. So the targets that we're choosing aren't necessarily going to be high in the sky to those assets. So we have to take then look at what is the possible degradation of performance, and can we truly see the spacecraft for what we're going to need for tracking I apologize. I believe that should be minus 22 degrees for the baseline instead of minus 20. But what you can see here is overall the effect of where we're choosing that target versus how well is that ground station or that ground station complex in the NGVLA case is going to be able to track the spacecraft. These were all calculated, by the way, to a 35-degree latitude, which is close to the sort of the center of the NGVLA. It happens to be DSS 14 because it's a very easy calculation to run. So you can see even for that baseline case, it's not going all that high in the sky. It's going up to about 35 degrees. We do have 7.5 hours visibility of this on the spacecraft per day from that latitude. But this is something to take a look at, and this would be future work is, okay, what penalty would we have to assume then if our tracking never really gets particularly high in the sky? The ecliptic longitude plays into this quite a bit because of the tilt between the ecliptic coordinate system and an equatorial coordinate system. Overall, the impact here to us is That elevation above the horizon is going to determine the ground station's gain, its system noise temperature, and the atmospheric loss that we're going to see on the signal. Okay, next slide, please. Okay, next we took a look at what would we use for the solar or berth maneuver case. So the first thing that becomes apparent is that it gets harder to fly a big dish. The aperture size is now being limited by that thermal shield. Now, cases where your aperture limited is sort of the classic case where you would want to move higher in frequency. If you take a look at like the Parker Solar Probe, which has a very small high gain on it, Ka band operation was a game changer for the mission. It was absolutely necessary for enabling the kind of downlinks that they could get out of such a small dish. So the same thing applies here. We would really like to be running this at Ka band, not at X, but we still have to meet the tighter pointing requirements that are imposed by now going to Ka band and getting that higher directivity out of that dish. Next slide, please. The other consideration here for the solar or berth maneuver is that you now have a significant inner solar system component to the mission. So you've got to fly that whole portion of the mission where you're flying out to Jupiter and then coming back to the sun. So there is the tracking for in support of navigation for this, the TCMs in preparation for the solar or berth maneuver. In a lot of ways, this kind of breaks down to just two separate missions. The before the maneuver and after the maneuver. And in operations in the inner solar system, your spacecraft attitude is quite often dictated by concerns other than pointing the antenna. So we can't just swing around and point that high gain to Earth. So also, you're also often requiring kind of large swaths around the spacecraft of visibility and contact. So our Parker Solar Probe, for example, uses fan beams that cover an entire half plane around the spacecraft. And operation in that scenario, you're now pattern limited, which means that higher frequency operation is now at a disadvantage. So overall, this is going to lead to a more complex system. Sort of the straightforward approach here is to actually do a dual band system. Knowing full well that chances are portions of this system are not going to be used after we conduct that maneuver. Okay, next slide, please. So this is what something like that would look like. This is now a dual band XKA system. You can sort of see the tracking through that trade space again. We know we're going to have to do secondary pointing. We're going to have to sort of add that component now to the spacecraft where the telecom subsystem is more actively pointing that beam towards Earth than what we can get out of just the spacecraft attitude control. So, oh, I'm sorry, I did not change the number on the high gain. That is actually a 2.28 meter antenna. We went ahead and for mass calculations assumed that this would be a solid antenna. Again, though, there are things that we could do that have flown that we can use to bring that mass down. You can see that our downlink data rates here are commensurate, basically, with what we were getting with the XBand system. In fact, a little bit higher. Next slide, please. Okay. The power available for the science return. We had discussed this at the last workshop. If we design to that 50-year point, you can see how the power is allocated between basic components here, and we're sort of split, between the power required to generate the data we're sending down and the power it's taking to send it down. That's split between the science payload and what's going into driving those power amps, the TWTAs. And at 50 years, we're still maintaining a healthy margin, assuming that we're running, we've got those both RTGs going. In the case of a failed RTG, we would have to scale back power significantly. And one of the questions was, do we design for that case? For the baseline, we're designing to the 2 RTG case. So one of the things that we looked at is, okay, how far beyond 50 years could we actually take this? Go to the next slide, please. So looking beyond 50 years, if we do a sort of progressive decommissioning of instruments, as the available power from the RTG is degrading, and while we're decommissioning instruments, since we're cutting down the amount of the data we need to send down, start dialing back the power of the RF system as well to match. Now, with current technology, if we're flying TWTAs, they rapidly get inefficient if they're not operating close to their saturated output power point. There's a sort of a static DC draw that just goes into keeping the amplifier on. This is, you know, the heaters and the for the tubes and the anode current. You can dial back their power, but you will always have that sort of static draw there to deal with. Assuming that we do that, and assuming we stick with TWTA as we're showing here, you actually can get out to about 123 years life. This, by the way, is making one big assumption, and that is that RTG power that's available to us does follow a simple exponential. I would very much like to have a more detailed model of what we could do here and what we could expect from the RTGs. Go to the next slide. So one other thing we took a look at is I would really rather have another power amp technology here. And this is an area that I see is ripe for innovation, is give me something that I can give that flexibility of being able to dial back the power and maintain a higher efficiency. And there are technologies for doing this. There's different amplifier topologies. Could solid state amps actually compete here? It's hard to beat a TWTA for efficiency, but solid state is starting to get there. And also, are there space combining techniques that we could use to give us that flexibility? The one caveat I would say there before we jump directly to phased arrays is what can you do to maintain the aperture efficiency of the antenna while you're dialing back as well? But you can see here, if we could hold on to that TWTA efficiency of about 58%, you're now starting to get very close to 1000 AU operation. Again, assuming that the RTGs roll off following that exponential. Next slide, please. Okay, so overall, we've got a baseline mission that's accommodated with a very low risk, high TRL system. The solar rebirth maneuver design could be accommodated. It's introducing higher complexity, but again, it's complexity that is within reasonable bounds of available technology. There is ample room here for innovation. The sharing of large apertures with the radio astronomy community, I think, is key. So we will always benefit from having more aperture on the ground for a mission like this, and this is going to be a key enabler for this mission. And then improvements as well in beam pointing, most significantly showing that it can meet this lifetime of over 50 years. And then lastly, what can we do to be getting more flexibility and maintaining high efficiency in our downlink? I think I ran right up to my time limit. If I can take, I guess, one question, Marshall, the visibility per station per day. That you probably could interpret that as per network per day. And in this particular case, actually, no, I would take that actually as per station per day, because if you were to bring in other stations around the world, they would be phasing in basically as the Earth turns.
Thank you, Dave. And yes, we are right up against the break. If you do have questions, you can put them in the chat. We will continue to collect them and answer them. And I believe that Tony Freeman's question about active pointing of independent spacecraft, I think you did address that in some of the discussion that followed.
Yes.
But we can certainly continue to take questions on the Q&A side. and type answers in if you are curious. So with that, we are going to take a 10-minute break. We'll be back at 11:20 with Gabe Rogers, who's going to talk about guidance and control, which you already know is well coupled into the communication side of things. And we'll hear some more about that on both ends. So thank you all. We'll see you at 11:20.